Hello and welcome to my lecture series for Control System 1. Myself, Suman Ghosh, as a course coordinator, assistant professor from Guru Nanak Institute of Technology, Kolkata. And this course is designed for 5th semester BTech electrical engineering students. And this particular PPT is prepared or designed for lecture 3 and lecture 4. And in our syllabus, in module 2, that is mathematical modeling of dynamic systems, the following subtopics are writing differential equations and determination of transfer function of model of various physical systems like translational and rotational mechanical systems. Next, basic electrical systems and transfer functions, liquid level systems, electrical analogy of a spring mass damper system. Next, block diagram representation and signal flow graph using Mason's-Kane formula. And in this particular PPT or in this particular session, that is for lecture 3 and lecture 4, the contents are translational and rotational mechanical systems and some workout problems. So moving to our next slide, there is component of mechanical system. Mechanical systems are of two types. One is translational mechanical system and another one is rotational mechanical system. In translational mechanical systems, motion of a body takes place along the straight line. That is, motion or the mass is moving along the straight line. But in rotational mechanical system, motion or rotation of a body takes place along a fixed axis. That is rotational mechanical system. Now, first is translational mechanical system. In translational mechanical systems, there are three types of basic elements, that is spring, mass and damper. And in our next slide, we will discuss the three basic different elements and force generated by these elements. So moving to our next slide, that is translational mass. In all mechanical system, mass exists. In all mechanical system, mass will be there, and mass is an inertia element. Now, if we apply a force F, capital F, in a mass that in a body with mass m, and the body is moved and with a displacement, body is moved with a displacement of x, then according to Newton's law, force is equal to mass into acceleration. We all know that force is equal to mass into acceleration. So, and the mass will be capital M and acceleration is equal to d2x by dt square, where x is equal to displacement of the mass. So now dx dt is equal to v, that is velocity. So we can write it as f is equal to m dv dt, and like this we can write m into x double dot. X double dot means d2x by dt square. So force generated by mass is equal to m x double dot. Next is translational damper. Now we all know that all the materials has a property of damping to some extent, but when the velocity or drag is not negligible, that means there will be some friction, then we often model them with the damping force. Now, reaction damping force is equal to damping coefficient, that is capital B, into relative velocity of the two ends of the dashpot. So, by equations, we can write it as reaction damping force is equal to capital F is equal to damping coefficient, that is capital B, into relative velocity of the two ends of the dashpot. Relative velocity means x1 dot minus x2 dot, where x1 dot is equal to dx1 by dt, that is velocity of end 1, and x2 dot is equal to dx2 by dt, that is velocity of the end 2, where b is the damping coefficient in Newton per meter second inverse. Okay, so here the main thing is damping force is equal to F is equal to B into x1 dot minus x2 dot, that is damping coefficient into relative velocity of the two ends. And here is some common use of dashpot. We can use dashpot in door stoppers, vehicle suspension, bridge suspension, flyover suspension, like this. Next is translational spring. Translational spring is a mechanical element that is deformed by an external force, so that and its deformation is directly proportional to the applied force. Okay, now if the applied force is capital F, then the reaction force will be stiffness of the spring, that is small k, which is in Newton per meter, multiplication of amount of deformation of the two end of the spring, that is reaction force is equal to capital F is equal to stiffness of the spring, that is small k, into deformation of the spring in two end, that is x1 minus x2, where x1 is equal to displacement of end 1 and x2 is equal to displacement of end 2. So the main equations is F is equal to k x1 minus x2, that is the force generated by translational spring. Here is some example. First, one simple spring mass damper system is there, that is restaurant plate dispenser. In restaurant plate dispenser, there there is a piston. There is a piston which acts like a damper, and there is a spring, and the plates over the piston is acts like a mass. So this is basically a spring mass damper system. So in our problem 1 here, we have to find the transfer function for this spring mass damper system with a force F and displacement x. If we apply a force F, then there will be a displacement of x. So how we can solve this type of problems? We have to know. This is very important. And how we can find the transfer function of this type of problem? First of all, we have to draw the mechanical circuit diagram. In our problem, mechanical system will be given, But we have to calculate, we have to draw first the mechanical circuit diagram. Now how can we draw mechanical circuit diagram from that mechanical system? So there will be some assumption or some process. So what will be the process? First, the fixed end of the B and K. B and K means damper and spring. The fixed end of damper and spring are considered as reference point, and the reference points are represented by ground symbol. Okay, ground symbol is represented by ground symbol, and the lower end connected to the mass is considered as a node. Okay, one more thing, the number of displacement present in the figure will be the number of nodes of the system. And for developing a mechanical circuit diagram, the lower end of the mass is also considered as a fixed point. So the one end of mass will be connected to the fixed point that is represented by reference or ground symbol, and one end is connected to the node. Okay, and the number of nodes will be the number of displacement represented in the mechanical system. So just look at the mechanical circuit diagram in the solution. That is, there the number of displacement is 1, that is x. So the number of nodes will be 1, that is x, and there will be a reference point that is represented by ground symbol. So there will be a node x and there will be a ground symbol. And how we connect B, K and M and F? So as we already say that one end of mass will be connected to node, that is x, and one is connected to the reference point that is represented by ground symbol. So mass will be connected between x and ground symbol. Next one end of B is connected to the reference plane in the mechanical system. So one end is connected to the ground in mechanical circuit diagram, the other end is connected to the mass, and the mass is connected to x. So we have to connect the other end of B to x. Like this, we connect K, one end of K to reference point, that is ground symbol, and one end we will connect one end to x, and the force is connected to x and reference plane. And the direction of force, now what will be the direction of force? The arrow, in which direction? Now if we apply a force in which direction, then the displacement will be that direction. If we apply a force from left to right, then displacement of the mass will be from left to right. So the direction of force will be given, the direction of force, the arrow of the force will be given to the direction of x. Okay, so from this way we can draw the mechanical circuit diagram. Now from this mechanical circuit diagram we have to write the force equations. Now the force equation, now in this mechanical system we apply force small f, and the force is distributed over B, K and M. So the total force is equal to force generated due to M, that is mass, that is m x double dot, plus force generated due to damper, that is b into x dot, and force generated by k, that is spring, and that will be k into x. So our force equations will be F is equal to mx double dot plus bx dot plus x kx, or we can write this as m d2x by dt square plus b dx dt plus kx. Now what we have to find? We have to find the transfer function of the system. Now what is the definition of transfer function? Now the definition of transfer function is the Laplace transform of output divided by Laplace transform of input with all initial conditions to 0. Now in this mechanical system, what is output and what is input? In this mechanical system, here we apply force, that's why the displacement occur. So displacement is occurring, so displacement is the output, and here we apply force as a excitation, so force will be a input. So we have to calculate the transfer function, that is the ratio between displacement and force in Laplace domain. So we have to calculate x by f in frequency domain, that is in Laplace domain. So the equations we get, the equation we already get, that is f is equal to m d2x by dt square plus b dx dt plus kx. Now we apply Laplace transform here and we get m s square plus bs plus k into x s plus is equal to fs. So from this we can calculate xs by fs is equal to 1 by ms square plus bs plus k. So it is our desired transfer function which we have to calculate. So this way we have to calculate the transfer function. The problem, which type of problem is given? You first draw the mechanical circuit diagram, then write down the force equation, then Laplace transform, then perform the Laplace transform of this force equation and arrange the equation by output by input in Laplace domain. From these steps you can calculate the transfer function of a given mechanical system. So moving to our next problem. So there are another more example was there. Okay, so in our next classes we will discuss some more problems and rotational systems, force due to rotational systems, and some more example on rotational system. So this is for today's lecture, or that is for lecture 3, and in lecture 4 we will discuss some more example. So thank you for watching.